Hello everyone and welcome to Lecture 6, Solutions, Solubility, Concentration, and Converting Between Different Concentration Units. This mostly covers OpenStack's Chapter 11, so sections 11.1 through 11.3, but there is a little bit of Chapter 6 review in here as well, so I will link those sections below. First, let's start just with reviewing our definitions. What are solutions? You should remember that a solution, in this case, is a homogeneous mixture. Remember the difference between heterogeneous and homogeneous. So a homogeneous mixture of two or more substances. There's a few key terms you should remember. First, solvent. The solvent is the largest component in the mixture, and it does the dissolving. Next is the solute. The solute is the smaller component in the mixture. It is being dissolved. So for example, sweet tea. The tea extract and the sugar, those are the solutes, since they are the smaller components here in our mixture. Then water, since it's present in the largest amount, would be the solvent. Now let's talk about phases of solutions. Now, water is a common solvent, plays a major role in biology and a major role in chemistry. Solutions in which water is the solvent are called aqueous solutions. So if you remember that state or that phase of matter, AQ for aqueous, that refers to a compound that is dissolved in solution, specifically that is dissolved in water, or water as the solvent. We're going to focus primarily on this type of solution. However, solutions aren't always aqueous, though. For example, the air we breathe is technically a solution in which it has gaseous solutes, so oxygen, carbon dioxide, water, the other trace gases like argon. They are in a solution where the solvent is a nitrogen gas, since approximately 78% of air is composed of nitrogen gas. Solutions do come in a variety of forms. The solute and the solvent do not necessarily have to be in the same phase. So let's think about what's an example of this. Let's just say you had some, like tonic water or some soda water or whatever, right? This is an example of a solution in which the solute and solvent are not in the same phase. So if we investigate the following solutions here, we start with that soda water. Our solvent is water, and the solute would actually be the gaseous carbon dioxide that's dissolved in the water. Air, we just mentioned, solvent would be the nitrogen gas, and the oxygen and the other gases would be the solute. With sweet tea, sugar, tea leaf extract are the solute. Water, once again, is the solvent. Something like Everclear, grain alcohol, it actually flips. It's 95% ethanol, which means ethanol is the solvent, and the 5% water is actually just the solute. All right, let's briefly discuss the dissolution process. So in this dissolution process, first we need to disrupt the solvent-solvent interactions. So in this case, water, right? Water, as we established, water would be a good example of this. We have the hydrogen bonding holding those water molecules together. So in order for something to get in there, for a solvent, or excuse me, for a solute to dissolve itself in the solvent, like water, for example, these solvent-solvent interactions need to be disrupted. And to break these molecules apart from one another, this process is destabilizing, meaning it requires the input of energy. Step 2, the solute-solute interactions also need to be disrupted, right? So if it was sodium chloride, for example, those ionic bonds need to be broken apart in order for the sodium and chloride ions to dissolve, to interact with the water molecules. So this, once again, is destabilizing and requires energy. Normally this input of energy, so to speak, would just come from the environment that the solvent and the solute are in. And then finally, step 3, our solute-solvent interactions are formed, and this is stabilizing and releases energy. So when now those free solute molecules interact with those free solvent molecules, we get solute-solvent interactions, like the ion dipole forces we learned about a few lectures ago. And so when these interactions are formed, this is like when a bond is formed. When a bond is formed, this is very stabilizing. It releases energy. Okay. So to broadly summarize these in terms of enthalpy, so thinking about what I just mentioned about how these two steps are both destabilizing, energy is required, we'd say then that enthalpy is positive. These two processes are endothermic. They require the input of energy. Whereas this third process, which is stabilizing and releases energy, this can be thought of as being exothermic. It releases energy, and so delta H, the enthalpy, is negative. So being broad here, we can say that delta H1 plus delta H2 plus delta H3 gives you the overall enthalpy change for the dissolution process. Now, typically a solute is soluble in a particular solvent if it dissolves or mixes uniformly into that solvent at a given temperature. This tends to be the case if that delta H solution is negative. So if the solute-solvent interactions are stronger or more stable than the solute-solute and solvent-solvent interactions. So we have an overall energy release. So basically, if the sum of these two terms are less than this term right here. So if this plus this is a smaller number than this number. So if this was 10 kilojoules, and this term was negative 20, or bad example, negative 30 kilojoules. So positive 10 kilojoules, negative 30 kilojoules. If you sum those together, that would give you a delta H of negative 10 kilojoules, which means that this dissolution process releases energy, and if it releases energy, it's likely to occur. Whereas a solute is insoluble if the solvent does not dissolve at a given temperature. So this tends to be the case if that delta H solution is positive. All right, so we're not going to look at actual values or actual numbers in this unit. I just wanted to broadly discuss this. This is a little bit of an overly simplistic way of thinking about this. There are other factors at play here besides just enthalpy, but this is generally a good way to predict solubility, just given this basic information about enthalpy. Now, the more general rule here, and a phrase you've probably heard before, like dissolves like. So two substances that have similar polarities and or similar IMFs are likely to be miscible, which means they will be fully soluble in each other. Since water is very polar, compounds that are ionic and compounds that are polar tend to be highly soluble in water. So hydrogen cyanide, for example, soluble in water because of its polarity. Whereas this compound, this would be hexane, C6H14. This compound is nonpolar, so it's insoluble in water. Or sodium chloride, these ions are soluble in water since they will interact with water via those ion dipole interactions. A few examples of like dissolves like vitamins. So some vitamins are considered to be water soluble. So vitamin C and all of the B vitamins, they dissolve in water. They are typically found in foods high in water, and excess is likely to be excreted in your urine as waste. This is why you'll often see like fruits, vegetables often have a lot of vitamins B and C because those types of food tend to have fairly high water contents. There are other vitamins that are fat soluble, so vitamins A, D, E, and K. So these are vitamins you often see in like dairy products, in fats, in oils, in meat. These dissolve in fats, oils, lipids. They are typically found in foods that are high in fat, and excess will be stored in your liver and fat cells. So if we look at these water-soluble vitamins, I've got 5 of the total 8 B vitamins are shown below, along with vitamin C, which is ascorbic acid. How many how many polar groups or polar bonds can you find in these structures? So if you look at all of these structures, I see probably some lone pairs here. I see a polar group here. I see a positive ion here, a potential polar group here. These nitrogens may cause the nearby carbons to be polar. I've got an OH group here. Some similar things going on here. Lots of OH groups, OH groups, OH groups, OH group. Potentially some polar structures. Ascorbic acid has multiple OH groups and polar structures. You can see all 6 of the vitamins listed here have OH groups, they've all got some polar bonds. They may even have ions in them. This is why they are water soluble. They're very polar, or they may even have ions. They're likely to interact with the polar water and thus be soluble in water. Whereas the fat-soluble vitamins, notice them down below here, not as many polar groups. I see in vitamin A retinol, I see an OH, but otherwise I see all carbons and hydrogens. The vitamin A precursor, beta-carotene, all carbons and hydrogens. Vitamin E, almost entirely carbons and hydrogens, just one OH group at the end, just one OH group at the end here in vitamin D3. Two double bond O's, but otherwise nothing but carbons and hydrogens in vitamin K here. So you can see they may have a polar group or two, but they are by far non-polar. And so because of this, they are more likely to be fat soluble, since fats are usually composed of long carbon chains like this. Okay, now saturation. There are 3 levels of saturation. So solubility is temperature dependent. At a given temperature, a solution will hold a maximum amount of solute. This is specific to the solute and solvent being used. So at a given temperature, the first term you should know is saturated. So saturated solutions, as the name implies, they hold the maximum amount of solute that the solvent can hold at its current temperature. If you try to dissolve more, it's going to leave some undissolved. You'll have a precipitate at the bottom of whatever container you are using. Then next would be unsaturated. So once again, as the name implies, unsaturated solutions hold less. They hold less than the max amount of solute the solvent can hold. So it could hold more solute. And then finally, supersaturated solutions hold more than the maximum amount of solute that the solvent should be able to hold at its current temperature. So how can we make a supersaturated solution? One of the best examples to go to here is sweet tea. So what is the better process here? A or B? Should we have hot tea, add sugar to the hot tea, and then chill? Or should we have hot tea, chill, and then add sugar to the cold tea? What's the common process here? If you live in the South or you're just generally familiar with sweet tea, you know that process A is the way we go about doing this. What we do here is we heat up the tea, and so when the tea is nice and hot, when water is hot, it's capable of holding more solute in it than when it's cold. So hot water can hold a greater amount of sugar than cold water can. So if we heat the tea up, add the sugar to the hot tea, and then chill the tea down, if you do this right, and if you do it without disturbing the solution too much, you can actually end up with a supersaturated solution, where what's going on here is if you carefully cool this down without disturbing the solution, you will actually have more sugar in the water than the water should be able to hold at this temperature. Now, if you wait long enough, you'll probably see some of the sugar will start to crash out of the solution. It will fall to the bottom as a precipitate, but if you drink it fresh, when that sugar is still dissolved, you get that nice, really sweet taste from that excess sugar in the water there. So this is how you would make a supersaturated solution. If you made the tea chilled and then added sugar to the cold tea, you're not going to be able to get as much sugar in your water. Any excess will just crash to the bottom. Okay, so in summary, saturation is a measure of how much solute is currently dissolved in solution relative to the maximum amount of solute that the solution could hold. Saturation depends on temperature. This, again, is why we make sweet tea by adding sugar while the water is still hot. An unsaturated solution contains less than the maximum amount, a saturated contains the maximum amount, and a supersaturated holds more than the maximum amount. Alright, next, dissociation reactions. So when ionic compounds dissolve in water, as we've discussed before, they dissociate into individual ions. So thinking about sodium chloride or ammonium nitrate, calcium chloride, aluminum sulfate, etc., they all undergo a similar process. When you take the solid, you introduce them to water, they break into their ions, and they will exist in the state of matter or the phase aqueous. So parenthesis AQ. The other thing you should pay attention to is if you have an ion that has a subscript, so like CaCl2, this subscript should become a coefficient in the dissociation reaction. You see a similar thing happening here, 2 aluminum ions, 3 sulfate ions. Now, a solution of sodium chloride in water, or NaCl, does not actually contain NaCl units. Remember that only dissolved Na plus ions and Cl minus ions are present in the solution. Substances such as NaCl completely dissociate into their ions in solution. These things are called, remember, strong electrolytes. Quick knowledge check question. Which IMF helps to drive the dissociation of ionic compounds in water? So pause the video real quick, see if you can come up with the answer to this one. All right, correct answer here would be ion dipole. It's the ion dipole forces that drive the dissociation of ionic compounds in water. All right, next, a little bit of review on electrolytes. So since ions are charged particles, if we have a solution that contains ions, that solution will conduct electricity. For this reason, compounds which dissociate into ions when dissolved in water are called electrolytes. So in the process shown below, solid sodium chloride dissolves in water, separating into ions. The dissolved sodium ions and chloride ions act as electrolytes. This forms an electrolyte solution. So remember that electricity is simply the movement of electrons. And so if your solution has ions in it, those electrons can utilize those charged ions to move through solution. Whereas if your solution does not have any ions, it will not conduct electricity, since there's nowhere for those excess electrons to go. So for example, pure water actually does not have any ions. So if you had pure distilled water and you could be certain there were no ions in it, it would not conduct electricity. The reason that we generally think of water as being dangerous and conductive is that most times water will have some sort of dissolved ions in it. Now, a solution of sodium chloride obviously has dissolved ions in it, and so it will conduct electricity. Next, non-electrolyte solutions. As a general rule, most molecular compounds, when we say molecular compound, we mean covalent. So compounds that have just, carbon, hydrogen, oxygen, nitrogen, etc., non-metals in them. Most molecular compounds will act as non-electrolytes. A non-electrolyte solution doesn't contain ions, will not conduct electricity. So the molecular compound C12H22O11, which is table sugar, this dissolves in water as shown in the equation below. So when it dissolves, it still goes from being in the solid phase to being in the aqueous phase. But what's important here is this entire compound, it doesn't break into ions. This entire molecule right here just dissolves as is. So the state of matter changes, but there are no ions formed. And since there are no ions formed, this solution is a non-electrolyte, and sugar water is a non-electrolyte solution. It will not conduct electricity. All right, let's watch a quick video here on electrolytes. So what this instructor is going to show is, first, right now he has these two probes. These two probes are attached to a current that's attached to a battery and is feeding into a light here. And so these two probes go into the solution. And so basically, if the solution is an electrolyte, the solution will functionally complete the circuit, and electricity will flow, and the light will light up or turn on. So the first solution he used here was just pure water, distilled water. So when he puts the probes into the distilled water, you see no current flows and the light doesn't turn on. Now what he's going to do is he's going to take an ionic compound. I think he just has some salt there, but I don't have the audio on myself, so I can't be sure. So he's going to dissolve an ionic compound, probably just salt, into the solution. He's going to give this solution a quick little stir to make sure that compound dissolves. Now he's going to put that solution back into the probes, and the light bulb lights up. So now the solution is acting as an electrolyte. It's completing the circuit, current is flowing, and so our light bulb turns on. All right, now he's got another beaker of distilled water, and he's going to take some sugar. So just some simple table sugar, probably just glucose, might be sucrose. He's going to stir it up to get that sugar to dissolve, or at least as much of it can dissolve. Puts it into the probes, and look, no current flows because there are no ions formed, and so this solution is a non-electrolyte. Last one he's going to work with is he's going to take a beaker of distilled water, and he's going to add a little bit of acid to it. So we talked about molecular compounds on the previous slide. We're going to discuss in a minute here. If you have a molecular compound that's an acid or a base, especially a strong acid or strong base, which he is using here, those dissociate into their ions. And so just adding a little bit of drop of acid forms ions in solution, and now the solution can act as an electrolyte and current flows. Okay. Now, in general, for a solid solute in a liquid solvent, as temperature goes up, solubility will go up. So again, in general, not always, this doesn't for sure apply to all cases, but in general, for a solid solute in a liquid solvent, as temperature goes up, the solubility will go up. So sugar dissolves better in hot tea, for example. However, in general, for a gaseous solute in a liquid solvent, as temperature goes up, the solubility will go down. So for example, soda left out in a hot car goes flat. So we have inverse situation here. Solid solute in a liquid solvent, as temperature goes up, solubility goes up. Gaseous solute in a liquid solvent, as temperature goes up, solubility goes down. Again, these are both general rules. There are exceptions to both of them, but you should understand the general rule here. So this is showing how solid solubility usually increases with increasing temperature. So we can see potassium nitrate, sodium bromide, potassium bromide, calcium chloride, sodium chloride. For these ones, as temperature goes up, their solubility increases. You can see there's a few exceptions here, however. And then with temperature and gas solubility usually decreases with increasing temperature. So as temperature goes up, solubility goes down. This has some pretty major implications in biology, especially in aqueous environments. This is why hot sodas go flat quicker. This is also one of the potential problems with that global warming, or essentially climate change is causing, is as the temperature of the Earth increases, we're going to have to reckon with the fact that there's a lot of CO2 dissolved in the oceans. A lot of carbon dioxide is dissolved in our oceans. If the temperature of the oceans increases, well, what we're establishing here is as temperature increases, gaseous solubility goes down. So temperature of the oceans goes up, solubility goes down, more of that CO2 is going to be released into the atmosphere. Okay, we're going to briefly go over Henry's law. This law states the concentration of a gas in a liquid, or basically how much gas is dissolved in the liquid, is proportional to the pressure of that particular gas in the space above the liquid. Concentration of gas in a liquid, so how much gas is dissolved here, is proportional to the pressure of that gas in the space above the liquid. So simple example, if we have a low gas pressure above the liquid, we're going to have a low concentration of dissolved gas in the liquid. Whereas if you have a high gas pressure above the liquid, you can be expected to have a high concentration of dissolved gas in the liquid. This is defined by the relationship C equals K times P. C equals the concentration of the dissolved gas, which is typically in moles per liter. K is a temperature-dependent constant, which is typically in units of moles over liter atmosphere. And then P is the partial pressure of the gas above the solution. Let's think about how this works in biology. This explains and predicts gas exchange across tissue in the lungs into and out of the bloodstream. So think about your alveoli, right? So your alveoli are those really, really thin blood vessels in your lungs where the gas exchange occurs. So if you have a high concentration of oxygen in your lungs, the higher the concentration the oxygen is in your lungs, the more oxygen gas that will diffuse and dissolve into the liquid into your blood and be taken up by your red blood cells. This is part of the reason why people will often have trouble breathing when they get to high altitudes, why it feels like they're struggling to breathe. Quite simply, at higher altitudes, there's lower pressure, there's less oxygen. If there's less oxygen in your lungs, there's a lower partial pressure of the oxygen in your lungs. Not as much oxygen dissolves into your blood, gets to your red blood cells, and goes to the rest of your body, and then you begin to feel those adverse effects of not getting enough oxygen to your critical areas. Let's look at a quick practice problem. This problem states the Henry's law constant for CO2 is 3.4 times 10 to the negative second molar over atmosphere at 25 degrees Celsius, what pressure of CO2 is needed to maintain a dissolved CO2 concentration of 0.10 molar in a can of soda? Okay, so here's our equation. C equals K times P. So you can see here, you're being asked to solve for pressure. What pressure of CO2 is needed? So I'm going to rearrange this equation to solve for P. So P equals C divided by K. C here is concentration of the dissolved gas, which was given as 0.10 molar. And K is the temperature-dependent constant, which was given here as 3.4 times 10 to the negative second molar over atmosphere. Notice that the temperature here is not actually used in the equation. If this temperature was different, then this constant would be different, since this constant is temperature dependent, but you don't actually use the temperature in your calculation. So the correct answer here would be 2.9 atmospheres. Next, because the Henry's law constant K is a temperature-dependent constant, its value will always be the same for a given gaseous solute in a given liquid solvent. So if we have a certain concentration C1 of dissolved gas at a certain partial pressure of the gas P1, we can calculate the Henry's law constant shown here, so K equals C1 over P1. Now, if we have a different concentration and a different partial pressure, but we're at the same temperature, we can establish that K equals C2 over P2, and then we can basically tie these two equations together, and we can say C1 over P1 equals C2 over P2. So this gives us a useful relationship to determine the new concentration of dissolved gas after changing the partial pressure, or vice versa. But again, it's important to note that this equation will only work if the temperature stays constant, because if the temperature changes, the constant K changes, and then we can't make this substitution and establish this relationship. Alright, so let's look at a practice problem. The solubility of a certain gas in water is measured at 0.745 grams per liter at a partial gas pressure of 1 atmosphere and a temperature of 20 degrees Celsius. What will the solubility of the gas be if the partial pressure of gas above water is increased to 4.50 atmospheres at the same temperature? I have a small hint. First, you do not need to convert concentration into molarity. While on the previous problem, I showed you the concentration in molarity, it's just a general concentration unit C. So if the units are not specified, the units for C2 will be the same as whatever units were used for C1. So I would like you to try this problem on your own, see if you can solve for the solubility of the gas when the partial pressure is increased to 4.50 atmospheres. Okay, and the correct answer here is 3.35 grams per liter. 3.35 grams per liter. So what you would do here is it's asking for solubility. So I would probably make my unknown C2, which would make P2 4.50 atmospheres. So then C1 is 0.745 grams per liter, and P1 is 1 atmosphere, and this would give you an answer of 3.35 grams per liter. Okay, so that wraps up most of the new stuff. We're going to finish this lecture by quantifying solubility. We're going to analyze the different measures of concentration. This is mostly Chem 151 review, but there's a little bit of new stuff in here as well. We'll get into more difficult calculations later in this lecture, but you should definitely review and practice with some of the formulas I'm going to go through here now. I'm going to go through these fairly quickly to get to the more difficult calculations, but definitely review some of these formulas if you feel like you need that review. So molarity, remember capital M, molarity is moles of solute divided by liters of solution. This is the most commonly used unit of concentration for aqueous solutions, and you'll see various problems with molarity. So the next couple slides here, I am not going to review or explain these problems. These are Gen Chem 1 review. If you need help with these, please reach out to me or review some of the Gen Chem 1 stuff, which you can primarily find in Chapter 6 of OpenStax. Okay. So I'm going through these pretty quickly. Feel free to pause at any moment and review these problems. Okay, here's something new. So I apologize if I went through those a little bit too quickly. You know what? Let me back up again. So if you don't care about this stuff and you want to get to the new stuff, then just hit fast forward on the PowerPoint slides by 30 seconds to a minute here until I get to molality. Molality is the new term. Let me go through these slides a little bit slower again. So again, the following 10 or so slides are reviewing some different concentration units you saw in 151, and they are showing some practice problems on 151. I am not going to review this stuff, but I'm going to go through these slides a little more slowly so you can pause the video and review this stuff and or try the practice problem on your own if you would like to. All right, so here's a new concentration unit you are not familiar with yet. It's molality. Molality. It also uses M. It uses a lowercase m. You may see me put a line underneath it to make sure you know that it's distinct from both molarity and mass. So molality is defined as moles of solute divided by mass of solvent in kilograms. So it's similar to molarity, right? Molarity is moles solute over liter solution. This is moles solute over mass of solvent, and it's specifically in kilograms. Molality is often used when precise measurements of concentration are needed across different temperatures. Note here the denominator is just the mass of the solvent only, and it must be in kilograms. For very dilute aqueous solutions at room temperature, molality is often equal to molarity. But molality is often used, again, across different temperatures, especially at high temperatures, because as you increase the temperature, the density of solutions will change. Solutions will get a little less dense as they heat up, which means their volume is actually typically increasing, but it depends on the compound we're talking about. Essentially, volume will change as temperature changes. So with molarity, that's a bit of a problem because with molarity, liter solution is on the bottom, whereas with molality, this isn't a problem. Mass of solvent is our denominator, and mass is not going to vary with temperature. So let's look at an example problem. This problem states, what is the molality of a solution that contains 0.750 grams of ammonia, NH3, dissolved in 125 grams of water? So molality is moles solute over mass solvent in kilograms. My solute is ammonia and my solvent is water. So I'm going to start by converting from from grams solute to moles using the molar mass of ammonia, NH3. Then I'm going to convert my solvent from grams to kilograms using this conversion factor. And finally, I will divide by each other, or divide the two by each other. Take the moles ammonia and divide by the kilograms water, and you get an answer of around 0.352 molal is how this concentration unit is referred to. So to summarize these concentration formulas, molarity, mole solute over liter solution, percent mass is mass of one part divided by total mass for everything times 100%. Mole fraction is moles of one thing divided by total moles of everything. And finally, molality is moles of solute divided by mass of solvent in kilograms. Okay, so the following slides are going to show you how to convert between different concentration units. I have a couple tips coming up here. I'm not going to walk through or explain the tips, but again, I will go through these slides slowly so you can have the opportunity to pause them and read through these on your own. All right, let's show you a couple of these difficult concentration conversion problems. Let's start with percent mass and density. This problem states household bleach is typically sold as a 5% by mass aqueous solution of sodium hypochlorite, NaOCl. What mass of NaOCl is present in a gallon of bleach if the density of the bleach is 1.093 grams per milliliter, or grams per milliliter? And you are also given the conversion you need of 1 gallon equals 3.7854 liters. Okay, so on these difficult conversion problems, I don't have the work on the slides, but I do have the answer in the notes down below. What I will do here is I'm going to give you a brief explanation as how you would go about solving this problem if you have trouble working it out, but I would encourage you to try pausing the video and coming up with the answer on your own. So I'm going to pause now. Okay, the correct answer here is 207 grams. There are 207 grams of NaOCl present in a gallon of bleach. How would you go about doing this? I would start with the volume I'm given. So I'm told that I've got a gallon of bleach. So I could take that gallon of bleach and I can get a volume in liters. So that would be 3.7854 liters. That's the volume of my solution, essentially. I would take that volume then and I would convert it to milliliters, so that'd be 3,785.4 milliliters. Once I've got that volume in milliliters, you can use the density here to find the mass of the solution. Once you have mass solution, you are given the percent mass. You can solve for mass solute. And here, the solute is the sodium hypochlorite, NaOCl. And you again should come up with an answer of around 207 grams. Here's the next problem, practicing with masses and mole fraction. So here is your problem. You have 3 kilograms of an aqueous potassium chloride solution containing 37.3 grams of KCl. What is the mole fraction of KCl in the solution? Again, I'm not showing the work on the slides, so I'm going to pause for a second and give you a chance to try and solve for this one on your own. Okay, the correct answer here is 0.003033. That is what I came up with. How would I go about solving this problem? Okay, well, notice that I am given the mass and the overall mass of the solution. I'm also given the mass of the solute. See how it says 3 kilograms of an aqueous potassium chloride solution, which contains 37.3 grams of KCl. What is the mole fraction? So mole fraction would be moles solute divided by total moles. So moles solute would just be moles KCl. So take your 37.3 grams KCl, find the molar mass of KCl, and then convert that to moles. And that goes up top here. The bottom is total moles, solute plus solvent. So again, you'll already have moles KCl from the first half of your calculation. How do you find moles solvent? Well, you need to ask, well, what is the solvent? We can assume that it's water since it says aqueous. How much solvent is there? You can take that 3.0 kilograms or 3,000 grams and subtract by 37.3 to get the grams water. Once you have grams water, simply convert to moles water using its molar mass, and then you can solve for mole fraction. Next problem asks you to convert from mass percent to molarity. You're told that bleach is a 5% by mass aqueous solution of NaOCl. It's got a density of 1.09 grams per milliliter, and you're asked what is the molarity. Once again, I will pause to allow you to try and solve for this one on your own. The correct answer here is 0.732 molar. So you need to find moles solute, and you also need to find liters solution. So now you're told you are given a mass percent and a density. Notice that you're not given a volume. So what I would do here, I think the easiest thing to do is to start by assuming 1 liter. Assume that you have 1 liter of solution, so right away you can put an easy 1 on the bottom. If you've got 1 liter of solution, you therefore have 1,000 milliliters of solution. If you have 1,000 milliliters of solution, you can find mass solution using the density. Once you have mass solution, you can find mass NaOCl, the solute, by using the mass percent, like we did a couple problems ago. And then finally, once you have mass NaOCl, you can find moles NaOCl using its molar mass, and you'll plug that in up top. And again, you should get around 0.732 molar. Okay, I've got two more problems for you. Converting from molarity to molality. This one states a 5.86 molar solution of ethanol has a density of 0.927 grams per milliliter. Calculate the molality of ethanol in this solution. I'm going to pause the video and let you try this one on your own. Or you should pause the video and try this one on your own. I'll pause here for a moment. Okay, the correct answer is 8.92 molal, 8.92. How would I solve this one? I've given a molarity and I've given a density. Once again, I notice that I'm not told anything else about the solution. If my starting quantity is a molarity, it's probably best to assume something about the volume of the solution. So I'm going to assume 1 liter of solution. If I assume 1 liter of solution, I can use the provided molarity to find moles ethanol, which will give me moles solute. If I've got the volume of the solution, I can find the mass of the solution using the density. Once I've got mass solution, I can subtract the mass of the solute to get the mass of just the solvent, which is what you need for molality. So that's how I would recommend solving this problem. All right, this one asks you to convert from molality to mole fraction. Calculate the mole fraction of solute and solvent in a 3.0 molal solution. Here, I would probably recommend making an assumption about the mass of the solution. If you have a 3.0 molal solution, you can make an assumption, about the mass of the solvent. You could assume 1 kilogram solvent to make the math easier for you here. And the correct answers: the mole fraction of the solvent, water, is 0.949, and the mole fraction of the solute, sodium chloride, is 0.0513. Okay, sorry, I still have 2 more questions. I thought I was almost done. This one is mole fraction to molality, so the reverse of what I just described. You are given just the mole fraction and asked to solve for molality. Again, you'll probably need to make an assumption here. The correct answer on this problem is 1.53 molal. And then the very last problem is going from molarity to everything else: percent mass, mole fraction, and molality. Correct answers here: percent mass would be 31.8, mole fraction is 0.1175, and molality is 7.39. If you had trouble with any of these conversion problems and you would like to see the work, please feel free to reach out to me via email, or if you're coming from outside of Wake Tech, feel free to send me a message on YouTube and I'll be happy to help you out with this, or you can Google me and find my email address. I apologize for not putting the work up on the slides, but would really like to encourage you here to try and figure these ones out on your own. Following the units, once again, will be a big help on solving these problems if you're having any trouble with them. But that's the end of this video. That's the end of this PowerPoint and the end of lecture number 6 on solutions. I hope you found this helpful. Again, please reach out to me if you have any questions at all, or if I can help in any way with you understanding this material. I hope you have a great day, and I will see you in the next video.